In this video we're going to be looking at the radius of convergence, and in our previous video we actually verified if a series was convergent or not, and we saw that it converged to a value of 1/4, which was less than 1, and we concluded it was convergent. Now in question B we have been asked to calculate the radius of convergence, meaning that we have been told this series converges, so it's directly telling us which method to follow, right? So it says determine the radius of convergence. So we are going to use a similar approach as the first as a solution to the first question. And yeah, so to do that we are going to name our series as usual. In this case it's a power series. Then we are going to have our AK to be the sum from k equals to 1 to infinity of x raised to the power k divided by k squared. We are going to look for our AK plus 1, and this will simply be the sum from k equal to 1 to infinity of x raised to the power k plus 1 divided by k plus 1, all that squared. Again, AK plus 1 simply means we replace k with k plus 1 anywhere we see k in our AK. So it's very easy. Now in this case we know our condition for convergence is that the limit, right, as k tends to infinity of the absolute value of AK plus 1 divided by AK should always be less than 1. Now for the sake of the length of the video, I'm not going to be writing down all the steps, especially the things I've already explained previously from A. So in this case we're simply going to go directly by substituting. So this implies that we're going to have the limit as k tends to infinity of, we know our AK plus 1 is our function above here, so x raised to the power k plus 1 divided by k plus 1 all that squared, and our AK is simply x raised to the power k divided by k squared. Now this is equivalent to x raised to the power k plus 1 divided by k plus 1 all that squared, now multiply by k squared divided by x raised to the power k. Again, I've taken the inverse of this, so I've switched the numerator and the denominator, and to further solve this we just need to simplify. We identify that we notice that we can actually simplify our x raised to the power k plus 1 to have x raised to the power k, so that we can easily cancel out. So x raised to the power k plus 1 can be written as x raised to the power k multiplied by x. I'll explain this in our previous video. And in the denominator we can simply have k plus 1 all that squared, now multiply by k squared divided by x raised to the power k. So this x raised to the power k can cancel out since it's the same term in the numerator and the denominator, and we'll simply be left with x multiplied by k squared divided by k plus 1 all that squared. What do we notice? We have k plus 1 squared and k squared, so we can actually write this as x multiplied by k divided by k plus 1 all of that squared. So we can do this because they have the same power, right? You don't necessarily have to do this. Alternatively, what you could do is to actually just simplify it normally. Simplifying it normally simply means here, so what I mean by that, it simply means we're going to have x multiplied by k squared divided by k squared plus 2k plus 1. So this is what you can alternatively have, and it's not going to change. And remember, we're looking for the limit, right, as k tends to infinity. So I wasn't writing this just to simplify the time, right? So remember, this is what we're looking for. What do we notice? Now we want our value of k tends to infinity. We notice that as explained previously, this limit is going to turn to 1, and we can write this as the limit, right, as the absolute value of x. Again, in this case our absolute value of x is a constant because it is not in terms of k. So as k tends to infinity, it's not going to affect the value of x. That's why in this case it's considered a constant, as I explained again previously. So we're only focused on this part of our equation, the absolute value of k squared all over k squared plus 2k plus 1. Again, this 2k plus this k squared plus 2k plus 1 is just an expansion of k plus 1 all that squared. You can do that like manually. And again, here the limit is 1. This limit, it's 1 as k tends to infinity, because the highest power of the degree of the highest power of the numerator is k squared, and the degree of the highest power of the denominator is also k squared. So as k tends to a very large number, this all of the entire function is all going to be affected by the degree of the highest power. So this limit is actually going to be 1, because if we factor out k squared, we are going to be left with 1 in the numerator divided by k squared. We factor out k squared in the denominator, we are going to be left with 1 plus 2k all over k squared plus 1 all over k squared. Again, 1 all over infinity, which is 1 over k, is all going to be 0. So 0 here, 0 here, will be left with, this will cancel out, will be left with 1 divided by 1 plus 0, which is 1. So that limit is going to be 1. So you have to know this, like you have to understand this rule. It's very, very important. So once you know that, we notice that all of this is going to simplify to be the absolute value of x. And remember that the absolute value of x needs to be less than 1. So once you arrive at this point, pretty much you're done with the solution. So our conclusion will simply be that the radius of convergence is 1. But of course, I'm going to show you how I got the radius of convergence to be 1. Notice that the radius of convergence of a series, in this case power series, is the value from the center of that series to any point of that radius, if we are to draw it on a number line for which that series will converge. Now if you solve this inequality, you're going to notice that the result is actually going to fall within this range. This is the solution if you solve this inequality, and this is basically from the definition of inequalities. For those who do not know, let me just solve that quickly. The definition of absolute value is x when x is greater than 1, and negative x when x is less than 1. So meaning that x will be greater than negative 1. So that's basically it. Multiplying with the negative here, we're going to have x. The inequality sign is going to, from less than, will be greater than, and our 1 will be negative 1. So inserting that, we're going to have this. So this will be the range of the radius of convergence. Now if we represent that on a number line, we're going to have 0 here, we're going to have 1 here, we're going to have negative 1 here. And if you imagine an imaginary circle, very funny, if you imagine like an imaginary circle around this, the radius of convergence is simply this distance from the center to the point where our series converge. So this is 1. It's the same, the distance is 1. So this is our radius of convergence. It's simply that range or that area in which our series will converge, and in this case it's all defined by the function, the absolute value of x. Now it could be any other function, it could be any other function here, it could be x squared, it could be maybe a parabola, a hyperbola, or any function, but it's not going to be that complicated at this level. But just know that in this case, once you have this value, the series of the radius of convergence is 1, as can be seen on the screen. So to do that, just simply solve your equation after simplifying it, and notice we're told that it converges, so you need to know that. So that's it for this video, and see you guys in the next one.